There are four basic properties of a gas. Pressure, which we use a capital P to represent, volume, capital V, temperature, capital T, and then we talk about the amount of gas in moles, which is represented by N. So the properties are interrelated. If you change one of them, it's going to change one or more of the other properties. And so there are a set of gas laws known as the simple gas laws that describe the relationship between just two of the properties, say volume and temperature, or temperature and pressure. And these laws were deduced from observations that actually occurred a long, long time ago, in which two of the four properties were held constant, and then they would change a third property and see how the fourth one reacted to that. So I'm going to be talking about the scientists that developed these laws. I am not going to test you on their dates of birth and death or their names, but I think we do need to acknowledge them. So Robert Boyle lived back in the 1600s. I said this was 1600s. This was a while ago. He used a J-shaped tube, and he was interested in the volume of gases in relationship to their pressure. So he would take this J-shaped tube and have some gas here and cap this off, and then look at the height difference, the pressure difference between the inside, the gas here, and the outside. So this is like a manometer, except the container we're looking at is really, really small. And then he could change the pressure on that gas by pouring more mercury into the open side of the manometer. So the mercury is going to be pushing down, and it's going to cause this side of the mercury to go up. And now the difference in the height of the columns is different. So now we have a greater difference in pressure than there was before. So he observed that if you increase the pressure on a gas, its volume gets smaller. It decreases, which kind of makes sense. If you think about a balloon, and if you were able to squish it and make, what would happen? You put pressure on it, it's going to get smaller, right? Because that's what gases do. You can compress a gas. You can't compress liquids and solids. So this was an inverse relationship. If one of those goes up, the other goes down. So here's an example of the sort of data you might see for a Boyle's law experiment. So changing the pressure on the gas and then measuring the volume of the gas. We see that the volume of the gas is high at low pressures, and it decreases as the pressure increases. So this is a curve, and it's much easier to develop mathematical relationships if you can do something to this and make it into a straight line. So if instead of graphing volume versus pressure, you graph volume versus 1 over the pressure, then we see that we get a straight line. So this is volume versus pressure, and if we do volume versus 1 over pressure, we get a straight line. And that can be described mathematically very easily. It's important to note that in order for this to be true, we have to keep the other two parameters or properties the same. The temperature has to be constant, and the amount of gas has to be constant. So as P increases, V decreases by the same factor, so we can imply that pressure times volume is equal to a constant. So this is how Boyle's law is usually expressed. P1V1 equals P2V2. The pressure times the volume in one set of conditions is equal to a constant, which will be equal to the pressure times the volume in another set, as long as you keep T and N constant. This is the molecular interpretation of Boyle's law. As the volume of a gas sample is decreased, then molecules are going to collide with the surrounding surfaces more frequently, resulting in greater pressure. So you can use the pressure to change the volume, or you can observe how a change in volume affects the pressure. Here we've got a gas in a cylinder with a pressure gauge here. Here the volume is equal to 1 liter, and we have 1 atmosphere of pressure. If we press down on the top of this container and make the volume smaller, so here the volume has decreased by a factor of 2, then the pressure increases by a factor of 2. The reason is that these gas particles are now confined to a smaller space. They're still zinging around, bumping into things, but because they're confined to a smaller space, they're going to bump into things more frequently, and so the pressure goes up. Boyle's law is important to know if you're doing scuba diving. So when you are swimming and you go under the surface of the water, you're going to experience more pressure than if you were just going down in air, because water is much more dense than air. So for every 10 meters of depth that a diver goes down, you're going to experience approximately 1 additional atmosphere due to the weight of the surrounding water. So you go down 10 meters and you're going to be experiencing a pressure of 2 atmospheres, double of what we're used to. So up here at depth 0, we've got a pressure of 1 atmosphere because that's from the air. We go down 20 meters, so going down 10 meters adds 1 atmosphere, another 10 meters adds a 2nd atmosphere, and so now we have a pressure of 3 atmospheres. A pressure of 3 atmospheres is going to make it very difficult to breathe, right? I don't know if you ever saw some of the old cartoons, and somebody's being chased, right? And so they hide under the water, and they've got like a straw, and they're breathing through the straw, right? If you're right close to the surface, that could work. If you're going down deep, I don't care how big that straw is, you are not going to be able to breathe, because you're not going to be able to expand your lungs against the pressure of the water around them. And so that's why in order to breathe at these depths, you need pressurized air. So if a diver is down deep and takes a breath and holds it and rises to the surface quickly, now the external pressure has dropped from, say, the 3 atmospheres that you had down at 20 meters down to 1. Pressure drops from 3 atmospheres to 1 atmosphere. So what should that do to the volume of the air in your lungs? Should expand, right? So if you were able to hold on to that, your lungs would probably explode. The good news is you really couldn't, right? You're holding your breath and it's just going to come out anyway because of all the pressure. But this is one of the reasons why they talk about always exhale when rising from under the water. Because what would happen if you went from 3 atmospheres to 1 atmosphere is that the volume of air in your lungs would triple in size. And yeah, lungs just aren't meant to do that. So I always think this is a weird first example of a gas law problem. This one's kind of tricky. I guess it's supposed to be interesting. Anyway, let's just do it. So this one really has a story. A snorkeler takes a syringe filled with 16 milliliters of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? Okay, this is one of those problems that students generally have kind of a hard time thinking about. And so this is where drawing yourself an ugly picture can help. Your pictures do not have to be beautiful. As long as you understand what you were drawing, that's good enough. So what we're talking about here is we've got a syringe. Well, that's not right. We've got a syringe that's got some air in it. Okay? So there's air in there. And up at the surface of the water, where the pressure is 1 atmosphere, that has a volume of 16 milliliters. And drawing people is harder, so I'm not going to draw the snorkeler. I'm just going to stick with the syringe. The snorkeler is going to take the syringe down deeper. As you take something down under the water, the pressure from the water increases. It increases a lot. And so that's going to push and compress this air, and so the air is going to get squished, and it's going to be smaller. So this is telling me that down at whatever depth this is, the volume is 7.5 milliliters. So I've got 16 milliliters and 7.5 milliliters, and I've got 1 atmosphere. And the first question they're asking is the pressure. So this is a Boyle's Law problem. That's Boyle's Law up here is kind of a big hint at that. But they're giving us pressure and volume information. And the way Boyle's Law is usually expressed is P1, V1 equals P2, V2. So what we need to do is to identify, well, what's 1 and what's 2, and what are the pressures and the volumes? Well, let's call 1 the thing that happened first. So this is when this syringe was at the surface of the water. And so I'm going to say, well, this is volume 1 then. Volume 1 is 16 milliliters. What is pressure 1? It's 1 atmosphere, right? They said that the pressure at the surface is 1 atmosphere. And so then this will be condition number 2. This is volume 2. And we don't know what pressure 2 is. That's what we're trying to calculate. So this equation has 2 pressures and 2 volumes. And we have 3 of the 4 pieces of information, so we can solve for the missing one. So I'm looking for pressure 2, P2. And so we want to take this equation and rearrange it before we put the numbers and units in. Okay? So there's a little bit of algebra involved here. In order to isolate P2, I need to get rid of the other things on that side of the equal sign. Pressure 2 is multiplied by volume 2. If I divide this side by volume 2, then V2 cancels out. In order for this to still be an equality, I need to do the same thing to both sides. So I end up with this equation that P2 is equal to P1, V1 over V2. And you can see how it'd be really easy to mix up your 1s and 2s, right? If you have a TI-36X Pro calculator, I can show you how to use a function on here so that you don't have to rearrange equations like this, right? You can just type the numbers in, make it look just like you've written it on the paper, and it'll do the algebra for you, right? I'm not going to get into that in the video because I don't have a good way to show that. But let's finish doing it the old-fashioned way. So I rearranged this equation, and now I'm going to take my numbers and plug them in with their units. Units are always really important. So pressure 1, that's this guy. So 1 atmosphere, and volume 1 is 16 milliliters. And then I'm going to divide by volume 2, down here, 7.5 milliliters. Let's look what happens with the units. I have milliliters divided by milliliters, and so the milliliters cancel out. So I'm going to have 1 times 16 divided by 7.5. So the pressure is 2.13 atmospheres. So expressing that as what is the pressure, we would round that and say 2.1 atmospheres. Because all of my other numbers have 2 significant figures, so my answer should have 2 significant figures. So that's the answer to the first question. So that's the first one. What's the second question? How deep is the snorkeler? Okay, this is the part that becomes a critical thinking problem. This is what makes this one kind of tricky. So it's reminding us that the pressure increases by 1 atmosphere for every 10 meters of depth. So up here at the surface, I have 1 atmosphere. And if I go down 10 meters, I'm going to have 2 atmospheres. And if I go down another 10 meters, I'm going to have 3 atmospheres. So this is the pressure, 2.1 atmospheres. And so we could look at this just, kind of sketch here and say, well, it's about 10 meters down, right? Because you've added an extra 1 atmosphere, but we can be a little more precise than this. So this is the pressure at that depth. What is the additional pressure that has been added? It started at 1 atmosphere. How much additional pressure was added? Well, we now have 2.133 atmospheres of pressure, and we started with 1 atmosphere. So we've added 1.133 atmospheres of pressure. And this is telling us that there's 1 atmosphere for every 10 meters. We're going to have to move up to the top. So that's the additional pressure, and for every 10 meters, there's 1 atmosphere added. The atmospheres cancel out, and so we're going to get an answer of the syringe was at a depth of 11 meters. Mm-hmm.
How deep could you go before that becomes the pressure becomes too much for a person to?
Well, so I don't know how far down you could go before it becomes. Well, I mean, obviously going down, there's the issue of you, unless you take air with you, you can't breathe, right? So if you're taking pressurized air with you, you can go down deeper. I don't know what the maximum depth is, but there definitely is a maximum depth where no matter how pressurized the air is, you're just not going to be able to breathe. And so that's why for the really deep sea diving, you have to take some sort of a submersible or something like that. Yeah.
Why did you subtract the 1? Oh, is it because you started at 1?
Yeah, so we weren't starting at 0 pressure. We were starting at 1 atmosphere. And so we're looking at what's the additional pressure. That's what makes this problem really kind of tricky.
Oh, yeah, no,
It's like
wait,
this.
I could've sworn they measured that, and they just like plug back in the grid.
I really should do something about this, but yeah, I always forget after class. Any other questions about this one? Another simple gas law looks at the relationship between volume and temperature, and this is known as Charles' law. And he lived in the 17 and 1800s. So he found that the volume of a gas was directly proportional to its absolute temperature. And so this is very important. When we're talking about gases, the temperature must always be expressed in kelvins. So Charles' law is often expressed like this: V1 over T1 equals V2 over T2, the relationship between volume and temperature. If the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. And this is where the idea of absolute zero came from and where the Kelvin scale came from. So here we're looking at the volume of gas as a function of temperature. And the top temperatures are in degrees Celsius and the bottom temperatures are in kelvins. So 1 mole of gas at 1 atmosphere, because we have to hold the amount and the pressure constant, we see that we have this relationship between volume and temperature. This is the smallest data point, and after this we're extrapolating, because we're going down to 0 degrees, the freezing point of water. Here's half a mole at 1 atmosphere, and here's a quarter of a mole at 1 atmosphere. If we extrapolate the data, extend it out, we find that these lines are going to intersect at a point where the temperature is equal to negative 273.15 degrees Celsius. And that's what we call absolute zero, because that intersection happens where the volume would be 0. Can you have negative volume? No. So think about the gas is cooling down, is getting smaller and smaller and smaller and smaller. It can't get any colder than 0 volume. Now, actually, we know that you can't get to 0 volume at all because the gas particles themselves have volume. But this is the theoretical lowest possible temperature. So we call that absolute zero, and all of the Kelvin temperatures are positive. There are no negative Kelvin temperatures. So looking at what the molecules are doing, if we take a balloon from an ice water bath and put it into boiling water, we'll see that the balloon will grow in size. What happened there? Well, the temperature went up, right? When the temperature increases, these particles are going to move faster, right? And so they're going to take up more space at the same pressure. The gas particles are going to move faster, and so we actually have two things happening with that. We have the particles colliding more frequently with the walls of the container, which would increase the pressure. We also have the particles colliding with more force to increase the pressure. So if we are maintaining the same pressure, the only way to maintain the same pressure is to allow the gas to occupy a larger volume. That reduces collisions to less frequent and over a larger area, so the pressure can stay the same. I remember being fascinated with balloons in general, but also with hot air balloons as a child. I mean, what kid doesn't like a good helium balloon, right? It's like things aren't supposed to float in the air, but here it does, and you can tie your little army figure to it, and he'll float up into the air. And I mean, like, how fun is that, right? And if you blow it up with air from your mouth, it doesn't do that, right? Well, then there's these hot air balloons. So we know that if we have a regular latex balloon and you put a hole in it, all the air comes out or all the helium comes out and the balloon collapses, right? If it was a helium balloon, it's not going to float anymore. So here we have this ginormous balloon with a big giant hole in the bottom. And it only has air in it, and yet we can make it fill up and then float up into the air, right? Sorcery. No, science. They've got these big gas burners that heat the air. Charles' law says that if you increase the temperature of a gas, its volume increases. The pressure inside the balloon is going to be equal to the pressure outside of the balloon thanks to this giant hole, right? As the gas particles expand, now there's fewer particles in that volume, and so the density of the gas goes down. So why do things float in water? Usually because the object is less dense than water, and so it will just float on top of the water. If we make the air in this balloon less dense than the air around it, it will also float. And we can get it to float and pull people up as well. That's why a helium balloon will float, because helium gas is much less dense than air, even at the same temperature. So, any questions?
Is there any way to heat up that air inside the balloon without having a big fire, like a fire like that, like jet
Is there any way to heat the air without having a big
flame?
flame? There probably is. There probably is. I mean, because that just looks kind of dangerous, doesn't
I
it?
was thinking when I was like, big jet.
Yeah. Yeah, I mean, you definitely, I guess you could roast hot dogs or something. Yeah. But, yeah, I'm sure there are other ways. But then you think about, well, what are you going to power this heating source with? If it's electric, then you're going to have a battery,
Yeah,
or it's a generator, and that's going to be really heavy. And so the advantage of, like propane or something is you get a lot more heat for the mass that you're having to also lift up. It's a good question.
It's made of like flame, like resistant material. Is that?
I would hope so. I would hope so. I think probably where you have to be the carefulest is when you're initially inflating the balloon, because once it inflates, the air inside is holding it away from the flame, and it's not going to collapse again until you turn the flame off, right? So then you're okay. But yeah, I'm sure there's been a lot of balloon accidents. Okay, so this is a Charles law problem, and this is a more straightforward type of gas law problem, unlike that previous one with the syringes. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? Okay, so we're going to stick with our habit of reading the entire problem, highlighting the numbers, identifying what they're asking us to find, and then figuring out what to do with it. So for the most part, gas law problems are going to be solved using equations. There is a way to solve many of these with a ratio method, and if you're interested in that, I can show it to you, but I found that it doesn't work for most students, so I quit talking about it, honestly. So we're going to have, with these gas law problems, we're going to have pressure, volume, temperature, moles, and we'll often have condition 1 and condition 2. And so it can be kind of crazy labeling all these things. So I find it's helpful to just make a little table. So make a little table to write these things down and keep them organized. So the top row will be 1 and the bottom row will be 2, and I'm just going to put things in here as I find them. So I'm coming up here, initial volume of 88.2 milliliters. So that would be condition 1, 88.2 milliliters. And then which of those quantities is that? Pressure, volume, temperature, or moles of gas? Well, it's volume, right? They even told us that, but the unit also tells us. So that's the starting volume, and then it says we're heating the gas from this temperature to that temperature. So 35 degrees Celsius is its temperature in the beginning at 88. So this is going to be my temperature column. I'm going to start at 35 degrees Celsius, and I'm going to go to 155 degrees Celsius. And that's going to leave one box empty. I'm going to call that volume 2. And that's going to be our final volume. What is wrong with what we've got so far? The temperature has to be in kelvins, okay? One way to think about this is if we had temperatures in Celsius, then we could have a negative temperature, right? And so then if we use that gas law, we could end up with negative volumes, which are not possible. So got to be in Kelvin. So we need to convert these to Kelvin. So that's 308 Kelvin. Let's make my table longer. And 155 is 428 Kelvin. So I need an equation that relates volume and temperature. So that's Charles' law. V1 divided by T1 is equal to V2 divided by T2. The equation's always, if it's given to you, it's going to be given like this. And I understand why, but it also really messes students up because a lot of students have trouble with fractions. So when we need to rearrange an equation that has fractions in it, I highly recommend getting rid of the fractions first, and we can do that by cross-multiplying. So cross-multiplying is I'm going to take the top of one side and multiply it by the bottom of the other side. So V1 times T2, that's going to be equal to the bottom of the first side times the top of the other side. Remember seeing something like that in math class? Thank you. So if we cross multiply, we can get rid of the fractions, and now we can rearrange it. I am looking for volume 2, that's this guy over here. So I'm going to divide both sides by T1, so the T1s cancel out on that side and go over there. There are lots of different ways to think about rearranging problems like this, and I'd be happy to talk to you about that. So now we have our equation. V2 is equal to V1 times T2 divided by T1. So in showing your work, the minimum that you should show is your rearranged equation, and then with the numbers plugged in like I'm going to do right now. So volume 1, we have it all organized in the table there, is 88.2 milliliters. And then T2 is this guy down here, 428 Kelvin, divided by T1, 308 Kelvin. And we look at the units and the kelvins cancel out, which is real nice. Would be a problem if it didn't. 88.2 times 428 divided by 308. 122.56 milliliters. So 123 milliliters. The temperature went from colder to hotter. Do we expect the volume to go up or down?
Go up.
We expect it to go up, and it went up, so that's encouraging. If you get things twisted, it'll go the opposite direction, and that can alert you to there's a problem somewhere. Any questions about that one? You should have done things like this in Chem 3A. 123 milliliters. Okay, so here's one of those thinking questions. The pressure exerted on a sample of a fixed amount of gas is doubled at constant temperature, and then the temperature of the gas in kelvins is doubled at constant pressure. What's the final volume of the gas? Well, there's all those choices. So this is how I would approach this. So we've got the pressure doubled at constant temperature. What does that do to the volume? If the pressure doubles, is the volume going to get bigger or smaller? Smaller. So that is going to cause our pressure to be divided by 2 to get smaller, right? And then it says the temperature in kelvins is doubled at constant pressure. So if I double the temperature, is the gas going to get bigger or smaller? If you heat up a balloon, does it get bigger or smaller? It gets bigger, right? So if I double the temperature, I should double the pressure. So that's going to multiply the volume by 2. So whatever that first volume was, they didn't tell us, right? Doubling the pressure is going to cause the volume to get cut in half, and then doubling the temperature is going to cause that reduced volume to double, and I'm going to end up with the same volume, right? Didn't mean to do that. So, E is the correct answer. The volume, final volume of the gas is the same as the initial volume. Those problems can be challenging. Most students would prefer to just be given numbers and asked to calculate something. Yes?
Just double checking, in this problem, it's talking, it just worded the temperature differently, but it's talking about the same temperature.
So it's talking about the first change is happening with no change in temperature. So there we're looking at the relationship between volume and pressure, and so that was Boyle's law. And then they're going to take that volume and keep the pressure constant and now double the temperature. And so that's going to cause the volume to double. And so those two changes cancel each other out. Yeah. That's a tough one. If you really, really just would rather do the calculation, you could make up numbers and do it, right? You could say, well, I'm going to pretend I had 1 liter of gas and the temperature was 100 degrees Kelvin and it was 1 atmosphere of pressure. And so you could calculate what does the volume become when you double the pressure. And then you could take those numbers and see, well, what happens if I double the temperature? And you would come up with the same number. So a third simple gas law is called Avogadro's law, and this is the same guy of Avogadro's number. He was the one to first formally state the relationship between volume and amount of gas in moles. The volume of a gas is proportional to the number of gas particles, not their mass or volume of the individual particles. So this was a big idea, that the volume is proportional to the number of particles, not other things. So that says that volume is proportional to N at constant temperature and pressure. And so we'll see this law expressed this way: V1 over N1 equals V2 over N2. We use moles to count the gas molecules, and so here we're looking at the volume is proportional to the moles of gas. So equal volumes of gas contain equal numbers of molecules, and what the gas is doesn't matter. And this is something that's particular to gases, doesn't work for solids or liquids, only for gases. So here's the volume of the gas, and here we're adding more gas to the container, keeping the pressure and the temperature constant. It makes sense. As you add more gas, the volume gets bigger. I mean, you think about a balloon. You put one breath of air into it. You put a second breath of air into it. It gets bigger, right? So add more gas, volume gets bigger. We can also extrapolate this and find that it goes to 0, 0, predicting that 0 moles of gas would occupy 0 volume, which, well, of course nothing would have 0 volume, right? So here's an Avogadro's law problem. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperature and that the initial volume of amount of gas completely reacts. That's like the fine print. So, this starts to sound like one of those problems where the train is going north at some speed and then there's an airplane and a helicopter and, all those weird problems they made you do in math class. Well, let's just highlight our numbers. We got 0.621 moles, we got 0.120 moles, and we have 2.18 liters. And the question is the volume after the reaction. So let's use a table to organize the numbers that we're being given. We'll have condition 1 and condition 2. So this is saying that it produces this much gas, and it's saying that it had this much before the reaction and that the initial volume is this. Most people want to call the initial volume condition 1. It actually doesn't matter, but it really bothers some people. So I'm going to recognize that this thing is coming after these. So the 0.12 moles and volume of 2.18 liters. Those two numbers go with each other. And that's really important that you have them with each other. If you stick this volume with that number of moles, you're going to get the wrong answer. So 0.120 moles, and that goes with 2.18 liters. So This column is N for moles of gas, and this column is V for volume. So it started with this, and then it produced this much gas. So that is the moles of gas. So 11.3 liters is the answer. We need to ask ourselves, does this make sense? So we went from a smaller amount of gas to a larger amount of gas. What do we expect the volume to do? Get bigger. You put more air into a balloon, it gets bigger, right? Did the volume get bigger? Yes. That's reassuring. Doesn't prove you're right, but it's reassuring. Any questions? Here's another example. This is one that's a little bit trickier. This would be a critical thinking problem. A scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. When 1.1 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. Well, let's highlight the numbers. Like that, and this, and this, and looking for the question. We're looking for how many more grams to make it rise. Well, we didn't have grams in the gas laws, right? They were moles. Well, let's make a table anyway and write down the numbers, and then maybe we'll draw an ugly picture, and then maybe it'll become a little clearer what we need to do. And this is going to be 1 and 2. So the blimp is going to rise when it has this volume. When 1.1 moles is added, the volume is this. So do you see that 1.1 moles and 26.2 go together? 1.10 moles and 26.2 cubic decimeters. We haven't really used cubic decimeters. It's okay. Spread them down and be fine. So this is N and this is V. And our other volume is 55.0 cubic decimeters. And it says when the volume gets to that, it's going to float. Well, just looking at this table, what could we calculate here? We could find the moles of gas at that volume, right? So the moles of gas that would cause it to float. Well, let's do that. Looking for N2. So that volume is equal to volume 1 times, that amount of moles is equal to moles 1 times volume 2 divided by volume 1. So starting with 1.10 moles and 55 cubic decimeters, divide by volume 1. Oh, look. The cubic decimeters that was kind of bothering us, they canceled out. Nice. 1.1 times 55 divided by 26.2. N2 is equal to 2.3092 moles with 3 safe days. Is that the answer to our question? No. But can we see how maybe we're getting to something that we can use to find that? So what this wants to know is, okay, so we had the 1.1 moles in there. How much more helium do we need to add? Well, they're asking it in grams, but I have the final volume in moles and the initial volume in moles, and so if I subtract them, I can get the volume added, or the volume that needs to be added, right? So 2.3092 moles minus 1.10. I don't generally advise doing that, but I did it. I'm gonna check. 1.2092. So that's the moles that need to be added. Could we find grams? Yeah, because that's moles of helium. So we can convert moles of helium to grams of helium using the molar mass of helium. .84 grams. Again, that's a kind of a tricky one. So in Chem 3A, you did problems with simple gas laws, but we didn't do stuff like how much was added. We didn't do things with the snorkeling and the syringes and stuff. We just did like, here's 3 of the things, find the 4th one.